Hello, everyone. Welcome back to the AAS YouTube channel, and this is part of the good stuff. This is the AAS Journal Author Series, and I am super happy to have Jesus Hernandez with us today. Hey, Jesus.
Hello, glad to meet you, Frank, and excellent for this opportunity. I am glad for
Well,
this.
thank you so much for being to talk about your very lovely AJ article, which we'll get to here very shortly. And Jesus, where are you located at? What's your geolocation?
I am working at the Astronomy Institute of the National Autonomous University of Mexico.
UNAM.
Particularly, I am in the institute that is located in Ensenada, a beautiful town near the bay in Baja California, Mexico.
Very nice. Very nice. Yeah, Baja is wonderful. Very cool. And it is July 6, 2023 as we record this, and I imagine that summer is in full swing in Ensenada.
Yeah, actually it's a beautiful, nice day today. Always is foggy in the evening, in the very morning, the night, and then the sun come out, and the bay is beautiful right now.
Lovely, lovely, lovely. I bet you get some good fish there too.
Yes, excellent, excellent food from the sea. Yes,
tacos, very good, awesome. And I'm in Phoenix, and it is way warmer here in Phoenix. We have definitely hit the power switch. So we are quite hot right now. So yeah, very good. And Jesus, what do you like to do for research?
Oh, well, my research focus in these last years on different aspects on the star and planet formation. Okay. Mainly characterizing and detecting young stellar population and their protoplanetary disk. Oh, yeah. And trying to link, observation with theoretical model using multi-frequency observations. Cool. And also trying to move from the high mass counterpart of the young star, that is the Herna star, to the low mass counterpart, that is the Tauri stars. Very nice, very nice. You cover the whole mass range. Yeah. Whole mass range, brown dwarfs to supermassives. And that is going to bring us to this very awesome AJ article. It is open access, people. You can go get a copy for free. We're in the open access era. Go get it. A LAMOST spectroscopic study of Tauri stars in the Orion OB1A Subassociation. And Jesus, take us away. Oh, thanks, Frank. Oh, yes, this work is based actually in an undergraduate thesis that Luisa Zamudio did in a university near here. That is the University of Baja California. Well, we have here also some people that the star-forming college know as Cesar Briceño and Nuria Calve, Shawan Shu. Other that are related to the LAMOST spectroscopic observations, like Hygo and Shaway. Okay. And some other people that work in this in the star forming groups, local star forming group here in Ensenada. Very nice. It's quite the international set of authors there. Very cool. Yeah, well, in this paper we use optical low resolution spectra to let me try to use this here. Okay. That's for bandwidth purposes, people. Yeah, to detect and characterize the Tauri stars that belong to the Orion star-forming complex. This Orion star-forming complex is a really interesting region that is used as laboratory in the study of star and planet formation. Particularly, this region have two main stellar association.
Okay.
One is the Lambda Ori stellar association that is located in the head of the Orion constellation. And the other one is the Orion OB1b, or OB1 association, that is located around the Orion belt. We can go to the figure 1 to see this.
Yes, that's a great idea. Let's get to figure 1 and we'll get a little bit of what we're looking at. Here we go.
Yeah, this show a map of dust that is green color with infrared. This map is from the infrared dust emission, and the red color represent the H alpha emission, and the isocontour represent the CO emission. Cool. So we can see here the Orion OB1 association, and this association are split into 3 or 4 sub-association. The Orion OB1A sub-association is located to the east of these yellow limits that are here, to the west of the yellow ring, and the Orion OB1V is in the Orion belt mainly, and the other that is the youngest and the more embedded region are the Orion OB1C and D, that is located toward the east of the Orion belt. So, traditionally, this association was assumed that have a sequential star-forming scenario that show a spatial temporal relation. Particularly, the Orion OB1A is older than the Orion OB1V, and the Orion OB1V is older than the Orion OB1CD. Okay. Now, recently, using Gaia data, several works report different kinematic structure in this association that don't support the sequential star-forming scenario previously suggested for this stellar association.
We have a mystery.
I mean that the scenario could be more complex than the sequential scenario proposed before.
Fair enough. Okay, let's dig in.
Okay, here we can see the 3 fields that we have in LAMOST. LAMOST is a spectrograph that can obtain 4,000 stars in a single shot.
Nice.
Of observation, and have a field of view of 5 degrees in diameter. This spectrograph is located in a Chinese observatory that with the same name, LAMOST.
Yes.
Okay. So our observation, we got 2 north field and 1 south field, and we got more than 17,000 optical spectra.
4,000 pop.
And this database includes many field stars, which are not the target for this paper. Thus, we need to reduce the sample, and we apply kinematic criteria to reduce the sample, selecting start with coherent kinematic using the parallax and proper motion of Gaia. And we can go to figure 3.
I am with you. Figure 3. So there's our figures. Let's get to figure 3 and parallaxes. Okay.
Yes. So
global.
Like in 2019, 4 years ago, more or less, we report more than 2,000 Tauri stars that we spectroscopically confirmed because this star have lithium in absorption, and lithium is a robust indicator of youth in low mass primary sequence star. I mean, spectral types K or M.
Yep, I'm with you.
So using this known Tauri star sample, we designed a membership box that is plotted here in gray color, in gray lines.
Yes.
And this is used to select kinematic candidates. Okay.
Yes.
But first of all, we apply a quality criteria to put stars or Gaia sources in this plot. We use we require that the uncertainties in parallax are better than 20%.
Okay.
And we also require that the Ruwe parameter is a quality parameter that tell us how well is the astrometric solution of Gaia. So the Ruwe parameter we require that is less than 1.4. That is the normal limit that the people use.
Okay.
So let's start with good astrometric quality are plotted here, and then we split the sample into 3 categories. The kinematic candidates start with good astrometric quality that fall within the membership region defined in Figure 3. Kinematic non-members start with good astrometric quality but fall outside of this membership box.
Okay.
And also start with uncertain kinematic status, which include stars that don't meet the good astrometric criteria that we apply. And of course, these stars were not included in Figure 3, but this is another sample that we have. Particularly for this sample, we perform a quick visual inspection of all the sample of all the 17,000 spectra, looking for stars that shows lithium in absorption. Independently of the kinematic status, if the star show lithium in absorption, we included as spectroscopic candidates.
Yes.
And we can go to table 1B, I think.
You know, I mean, 1B.
1B.
1B. Yep, gotta go up. Sorry about that. 1B. Here we go. Fields.
Okay. Yeah. And in this table, we can see the numbers of the stars selected as kinematic candidates and spectroscopic candidates in the 3 fields.
Okay.
Here we have 2 configurations for field 1 and 2 configurations for field 3, and only 1 configuration of observation for field 2.
Right, I'm with you.
Okay. Well, then we okay. Well, we already have the sample to be analyzed, so we go to the section 3.1a and apply the tool to characterize spectroscopically the sample.
Yes.
So we obtain spectral types, equivalent width of lithium, equivalent width of H alpha.
Okay.
And also we have a flag indicate the level of detection of lithium.
Fair enough.
A flag value equal to say that we have a very good reliable detection of lithium.
Okay.
Flag 0 indicate that there are no lithium in the, we don't detect lithium in the spectrum.
Okay.
And flag 1 indicate that, well, lithium is detected, but there are some doubtful, it's not robust, the detection.
Right.
So this analysis was performed with my code, the SPT class code that was, wow, many years ago. I did this.
Still works. It still works. It still works.
Okay, well, and then we use the H alpha emission, the H alpha equivalent width, and figure, let me see here.
We got H alpha. Finally, yeah, here we go. Okay.
Figure, that is what
Figure
is
4?
this?
Figure 4?
Figure 5.
Figure 5.
Yes.
Let's go to figure 5. Here we
go. Yes, with figure 5, we have a plot that tells us how is the accretion status of the sample selected using the lithium. I mean, I include here stars with flag lithium 1 or 2.
Okay. Gotcha.
So 4 years ago, we also found an empirical relation. We designed an empirical relation to split the sample into 3 categories or 3 types, depending of the accretion status.
Okay.
Stars that are located above the dotted line are classical Tauri stars. I mean, stars that have an accreting disk.
Yes, clearly.
Stars that are below the dashed line, the green dots, are weak Tauri stars. I mean, stars that is not accreting material from the disk to the star. And the blue guys there is a star that is just in the middle and could represent a star at the final phase of the accretion.
Okay.
And these stars are called slow accretor too.
Of course. Good. We have solid dots and open circles. What's the difference between those?
Okay. The solid dot is the bona fide T-Tauri stars. I mean, the stars that are kinematic member and also have detection of lithium with flag equal to. I mean, a robust detection of lithium.
Right.
These stars are the bona fide T-Tauri sample that we are going to use to make additional study later in this paper.
Okay.
Now I can go to the previous plot that is interesting.
Figure 4, we got effective temperatures.
Yes. So we have the spectral types, and we can convert these spectral types into effective temperatures using the pickup and Mamajet table conversion. And we can compare with other works.
Okay. Yes.
The main comparison here that I want to highlight is the comparison with the Gaia estimations.
Which is green. Okay.
The Gaia estimation used a set fitting method to obtain the extinction and the effective temperature and other parameters. But actually, this method have a problem because could include a degeneracy in the estimation of the extinction and the effective temperature.
Okay.
So here you can see the color dots that the larger discrepancies with all results that were obtained spectroscopically are for the stars with higher extinction estimated from Gaia. Okay.
Okay. I'm with
and
you.
this suggests that actually there is a extinction temperature degeneracy problem. Okay.
Okay, I'm with you. I'm following.
Yeah, and so we don't recommend use the Gaia extinction or Gaia affecting temperature for stars in star forming region because we have variable extinction. Okay. So this is the main conclusion of this plot.
I am with you. Very nice.
Okay, so I'm going to continue here. So we already have the effective temperature, so we can go further to obtain additional stellar properties. In section 3.2, we obtain extinctions, luminosity, masses, and ages using another code that I did that is I call mass age, okay, or massage. Massage.
There we go.
Massage.
We're gonna massage this data.
Massage
until we get a mass and an age. So, well named.
Yeah, it's a funny name. Oh, yeah. Okay. This code we obtain extinction comparing the Gaia and the 2-mass photometry color with the expected color because we have the effective temperature and we can estimate what is the expected color for the star. So we already have the extinction. With the effective temperature, we can also get the volumetric correction. And with the distance, we convert the apparent magnitude to absolute magnitude and obtain also the stellar luminosity.
Yes, I'm with you.
So we already have stellar luminosity and effective temperature. We plot the target in the HR diagram, and by comparing the location of the target with theoretical models, we obtain stellar masses and stellar ages.
Cool. Very cool.
In this paper, we use two theoretical models. Actually, massage has 9 theoretical models because time on the and other thing we only report here parsec and miss. Okay, and we can go to figure 6, and of course this method to obtain the masses and ages is model dependent. And we can see here that the ages and masses obtained by parsec are larger than the ages and masses obtained by MISS, particularly for low mass stars.
Yes, I'm with you. Yep. Okay.
Okay. It's important to mention that the uncertainties that we plot here are estimated using the Monte Carlo method of error propagation. So we run the code several times, varying the inputs within the uncertainties, within the error bars. Okay, at this point, we have extinction, effective temperature, luminosity, masses, and ages for the study sample, including the very, very important bona fide Tauri stars. And using this bona fide sample, we perform analysis described in figure A. Figure A, yes.
Okay, figure 8.
Color, okay. Yeah.
This one.
Yes, in this plot, we use or describe we apply the HDB scan clustering algorithm and detect 4 kinematic groups. Yeah. 2 in the north fields and 2 in the south field. Okay?
I'm with you.
Mm-hmm. Yeah. And we use, as you can see here, 3-dimensional space. Mm-hmm. Parallax or distance, proper motion in declination, and proper motion in triascension. Yep. And also we designed, based on this clustering algorithm, a membership cube for each kinematic group detected in this for this algorithm, using this algorithm.
Okay. Memberships.
Okay, figure 9 show.
Okay, I'm with you. Okay, figure 9. Ooh.
Yes. Figure 9 shows the spatial distribution of these 4 groups.
Okay.
We call these 4 groups north near, north far, south near, and south far.
Yes.
So, as you can see previously, the main dimension that split the sample is the distance. Mm-hmm. Okay. And also, you can see also a histogram of ages using the parsec and using the MIST models.
Mm-hmm. Okay.
And this suggests that this north far group is the oldest group that we detect in this sample. Yes. Remember that this sample only includes bona fide Tauri stars. Right?
Yes.
Okay?
Yes.
Mm-hmm. Well, but we complement this study looking star beyond the LAMOST field and beyond the bona fide Tauri stars.
Okay. Mm-hmm.
So it's a good idea go to figure 14.
Figure 14. Let's slide on down. Ooh, this is a nice plot. Okay.
Yes.
Okay,
in figure 14, in the upper left panel, mm-hmm. we plot stars that we call the kinematic members stars, and it's basically we apply basically the same criteria that we applied for the LAMOST stars.
Yes.
But now we include all the stars that are described in the lower panels. Okay, all the stars that fall in this region.
Right.
Yes, and then we select as Tauri kinematic candidates those stars that fulfill the kinematic criteria.
Okay. And
also are located above the 30 million years isochrone and have BP minus RP color larger than 1. So these are our Tauri kinematic candidates.
Yes, they are. Okay.
And the histogram of distance reveals that we have a minimum in the distribution of the Tauri kinematic candidates.
Yes, you do.
This minimum is 385 parsecs, something like that. Yeah. And we split the sample into near and far, similar than we did in the LAMOST stars.
Yes.
The lower left panel shows the numerical density map for the candidates that are located closer than this limit. I mean, the near sample. And we compare with the near sample of the bona fide T-Tauri star that we detected previously.
Yes. Okay.
So the near south group, I mean, let me show the bar. Okay, we can see that the north near group is associated with the non-stellar cluster already known, that is the 25 Ori stellar cluster, is with the HR 1833 cluster, and the other that is associated to the star 35 HD 35762.
Yeah, okay, I'm with you.
So, and also we can see that this kinematic structure associated with the north near cluster could extend beyond or south of the LAMOST field that we study.
Very clear.
Okay. Also, we have the north, the south near group, that is the blue dots.
Yes.
This group is spread out in all the field 1. Okay, as you can see there, and with a small concentration near the star HD 35456.
Right here.
Okay.
Okay.
What else? Also, we can see here that is not covered by the LAMOST observation, a strong kinematic structure in the Orion belt. I mean, in the region that we call the Orion OB1V association.
Correct.
Now, if we look the density map, but now of the farther sample, we see that basically the north far stars is more dispersed in the sky. And actually, this group is the oldest kinematic group detected in our bona fide sample, with more or less 10 million years in comparison with 6 million years with the other kinematic group that we detect.
Nice. I'm with you.
Okay. In contrast, in the south far group,
very clustered,
is mostly concentrated in the Orion OB1V subassociation. And this kinematic group could be related with this dense group detected in the Orion OB1V subassociation.
Okay.
Okay. So these results indicate or support the idea that the origin of this association, I mean the OB1 association, is more complex than we thought. Is more complex than the traditional spatial temporal star forming scenario.
Yes, right.
Okay, and this is one of the conclusions that we have in this paper. Well, now we also studied this population in this paper. Okay. Again, we use the bona fide T-Tauri star.
Yes.
And figure 11 show a plot in which we can obtain roughly this classification.
Okay.
Okay, here we have the stars located in the north field. I mean, in the south field, the right panel, the middle panel is the north field, and the right panel is theoretical models using irradiated disk mode.
Okay. Mm-hmm. Mm-hmm.
Okay, so the solid box
Yes.
is the locus of full disk in which we don't expect a strong erosion of the disk. I mean, the disk is mostly primordial.
Ah, okay.
And our synthetic color from our model is located in this box, mostly in this box, that confirm the full disk locus.
Okay.
Okay. Also, well, I also plot different the different accretion types in this plot. Also, below the solid line, we have the transitional disk types.
Yeah, that we saw earlier. Uh-huh. Okay.
We have only 1, 2, or 3, but these are really important type of disk because we have in this type of disk an inner hole, maybe, and this is my favorite scenario, maybe this inner hole is produced by a giant planet.
Okay. Okay.
Okay.
Yes.
So the dotted black box
yes
is the locus
Got it.
of the evolved disk.
Okay.
The evolved disk represent stars whose evolutionary effects on the disk are similar at different distance from the center of the stars. Thus, we can observe a global reduction of their infrared emission.
Right, which is what we want.
But this type of disk is primordial. The material in this disk is primordial.
Mm-hmm. Mm-hmm. So
in contrast, the other box that is below is the gray, exactly this box.
Mm-hmm. Right here.
Is the locus that you expect for debris disk or second generation disk in which the dust is produced by collisions and not from primordial material.
Okay. Very cool. Okay.
Okay. So this study is actually complemented with the appendix, in which we have the spectral energy distribution for each point plotted in this plot.
Oh, very nice. Okay.
So we can see more detail individually in each target. Sure. And there we have the yellow is the fluxes from the Gaia photometry. The green are fluxes from 2-mass photometry, and the red are fluxes from Gaia sources, from Gaia photometry. Okay. Mm-hmm. The solid line is the photospheric emission expected for the effective temperature that we estimate from SPT class. Right. And this solid region that is also with a gray zone is the expected full disk emission. And wow, this was constructed we did this full disk emission was constructed using stars in Taurus. That is a region that is younger than Orion, is 1 million years.
Okay.
Okay. Okay, so
A lot of SEDs there.
yes, a lot of HCD, and we can go, finally, we can go to figure 13.
Figure 15. Let's get to figure 15.
In this paper, we have a lot of HR diagram, but I am going to show you all these keys here, only the diagram of figure 13. 13.
13, I'm sorry. I missed my bad. Okay.
But yeah.
HR with bona fide.
Yes.
Money shot. Okay.
Yes. Here we plot only a star with good estimation of lithium detection.
Yes. Okay.
Okay. And the different color indicate different level of quality in the astrometric solution of Gaia.
Okay. Okay.
So the green dots show astrometric solution poor, I mean, not good astrometric solution with Ruwe larger than 1.4. And we use also another quality parameter here, that is the fidelity quality that was performed using machine learning techniques. But is more or less where we can use more or less similar than the Ruwe. The blue and the magenta dots are stars with good astrometric solution. And we can see here that the star with bad astrometric solution is systematically located above the good astrometric solution.
Yeah.
This could suggest that the green dots there have a significant fraction of binary or multiple stars.
We didn't cover that. Yeah. Very good. Very good.
Yeah. And this is not new.
Sure.
Actually, this is not new. Some people use the Ruwe parameter to detect bad astrometric solution, and they assume that are binaries. And so this plot agrees with the previous, with the use of Ruwe to detect binary, but the limit to detect binary is depend of the region, depend of the cluster. So we need additional observations to confirm actually if the stars are binaries or not.
Okay, we'll come back to that.
Well, I think this covers almost all the things that I want to share with you today.
Well, Jesus, I want to thank you so much for walking us through this very, very lovely AJ article. So thank you so much.
Thank you. Thank you for the invitation. I am going to turn on my...
Yes, please.
Okay, I am here.
You are here. Very cool. You mentioned it a couple of times, and I'll push on it a little bit. So where do you think we go over the next, let's say, 2 to 5 years? You mentioned the possibility of doing additional observations to determine whether it's binary or not. So are those observations ongoing? Maybe they're in the pipeline. Is there additional wavelengths one could look at to help distinguish this? Is there a need for different or better theoretical models? And just sort of where do we go over the next couple of years on this topic?
Yes, actually, I have a student, a PhD student, that is performing is performing a study, a kinematic study in Orion and in Taurus. Sergio Sanchez is my student. It's just starting, but he will use a Muse platform to perform many synthetic stellar clusters And also, he already have some clustering analysis in Orion, and we are detecting many substructures that are even more complicated than the structure that we see in this paper. Of course, we are going to cover all the Orion star forming complex, from the Lambda Ori OV association to the Orion OV1V association, including the ONC. And at the end, we want to put together the observations, the kinematic structure that we got from observation, and the theoretical models. In this way, we can try to get how this complexity of a structure were formed, and also we can see how we go to evolve in the future kinematically.
Right. There'll be other.
Okay. Also, I have another student in Colombia that is using machine learning techniques to detect Tauri stars.
Okay.
In LAMOST database.
Nice.
LAMOST is an excellent database, have a lot of spectra. Well, we want to, explain, to try to get the more Tauri star sample of this database.
Okay. Very nice.
And also here in San Pedro Marte, we have a spectrograph that can obtain a good optical spectra for a star brighter than 15 in visual.
Okay.
So we are going to complete all observations from of the kinematic candidate that don't have optical spectra, to also confirm the nature of these guys.
Very nice. Very cool. Well, I really look forward to seeing this field evolve over the next couple of years. It'll be very cool. Very nice.
But also the binaries, but
yeah, well, and the binaries, yes.
And the binaries.
Very definitely another big component. Very cool. Jesus, thank you so much for spending some time and talking about your lovely paper. It's really good.
Thank you, Frank.
And that'll do, everyone. And I hope this made your astronomy day just a little bit better. And we will see you on the next one. Bye-bye.
Bye.